Okay, thank you, Daniel. Thank you for the invitation. It's a pleasure to speak here virtually. So I'm going to talk about some applications of a mathematical formalism known as resurgence or resurgent asymptotics to some problems in physics, and in particular non-perturbative physics. And this is based on some work done with Mithat Unsal and my student Ahmed, and more recently with Vidya Kostin, who may even be in the audience. So let me start with some big picture motivation. There are lots of questions, as we all know, both mathematically and computationally about the path integral. I've written symbolically here the real path integral with the imaginary phase here. And on the right, the Euclidean path integral, which is the thing that we can actually treat more rigorously mathematically and also computationally using Monte Carlo techniques. So one of the interesting questions, of course, is what is the actual relation between the Minkowski and the Euclidean path integral? In the language of quantum mechanics, you can formulate this as a relation between a Schrödinger kernel and a heat kernel. And a couple of the really big problems where it would be much better to understand this in greater detail in quantum field theory, for example, are finite density problems at strong coupling where you can't just use perturbation theory. At finite density, even when you make this Wick rotation from Minkowski to Euclidean quantum field theory, because of the finite density, the chemical potential term remains complex. And so that causes serious problems for the interpretation of this Boltzmann-like factor as a probability weight for Monte Carlo. Similarly, if you want to do real-time dynamics outside of perturbation theory directly from the path integral, we really need to be dealing with this Minkowski path integral. And if we do computations in the Euclidean formalism, it's not a simple matter to analytically continue that back to the real-time domain. And there are lots of interesting problems ranging all the way from quantum chemistry to quantum gravity related to that issue. There are also more specific things related to studying phase transitions. If you interpret this path integral as something like a partition function for the quantum field theory, then using ideas from Li Yang and Fisher and company, we might be interested in how this behaves when the external parameters are complexified. So a common thread in all these questions is, what does it actually mean? And does it mean something rigorously and computationally to analytically continue a path integral? So that's the motivation. And just let's start off gently and recall a few things from ordinary exponential integrals to use as motivation and guiding principles. All the way back to Stokes, we learned that real physics in optics can in fact be governed by complex saddles of a exponential integral. And so the classic poster child of this phenomenon is the Airy function, which has an exponential decay on one side as x goes to plus infinity, but an oscillatory behavior as x goes to minus infinity. And if you look at this integral representation here of the Airy function, I want you to view that as some sort of zero-dimensional version of a functional integral, where you have an external parameter x, which you might think of as a mass or a coupling or a chemical potential or an external field or some parameter you can vary. And the idea is that there's no effective numerical method to compute this integral integrating along the real phi axis. So think of a phi as a real field. We simply can't do this using Monte Carlo or any other discretization technique numerically. Of course, we all know the solution. The solution is to deform the contour into steepest descent paths, and then it becomes a very simple problem. And Stokes's great insight was to realize that here only one saddle point contributes, but here we have a pair of real saddle points contributing to the integral. And of course, the message is that the contributing saddles and the behavior of the path integral, if you like, this function, Airy function of x, depends on critically on the phase of the parameter x. This is even more striking in the complex plane. So here's a plot of just the real part of the Airy function in the complex plane. Just to orient yourself, this is the real axis along here. I hope you can see the cursor moving. So there's exponential decay here, oscillatory behavior here along the negative axis. But you also see that there are these pi/3 Stokes sectors along this pi/3 and minus pi/3 direction. There's also oscillatory behavior. And along 2 pi/3 and 4 pi/3, there's exponential growth. And this can be seen in these connection formulas, which relate the area function to its behavior in these different Stokes sectors. So for example, if you rotate by 2 pi/3, you have this exponentially growing function, which is the other area function, but there's this exponentially suppressed other piece, and that's the guy we're looking for. Is there a way to be able to detect this exponentially suppressed contribution from standard analysis methods? So the moral here is that since even in these very simple solutions to linear problems where you have an exponential integral representation of the function, even in those cases, in order to understand the integrals, we need tools like complex analysis and contour deformation. It's at least a reasonable question to explore these sorts of methods in the infinite dimensional context of path integrals, where of course it's going to be much more difficult, but that's the background motivation. And I claim that a really satisfactory definition, or if you like, construction of a path integral should be able to describe this phenomenon of Stokes transitions. Now, I'm going to use tools from asymptotics, known as Resurgence. So to introduce this aspect, following that motivation, I need to introduce a few ideas from recent work pioneered by Jean Ecalle in the 1980s. And you can actually trace it back to an interesting observation by Hardy in this nice small book about orders of infinity, arguing that actually the only important scales in doing asymptotics are in fact logarithms and exponential functions. So this was a little bit vague in this book by Hardy, but he described grading of asymptotics. But this has now become a serious result in pure mathematics from Jean Ecalle. And to paraphrase it in just a short phrase, basically this is all we need, the logarithms and the exponentials and the powers. So there's an object called a trans-series, which I'll talk about more on the next slide. And it's generated from so-called transmonomials, these three basic elements. Think of h bar as a small parameter. So obviously we can have series which are powers of h bar. We can have series which are powers of this exponential factor, which we in physics might call an instanton or a non-perturbative contribution, and also powers of logarithms. And also include iterations. So there can be exponentials of exponentials of exponentials. There can be logs of logs of logs of logs. And the basic claim is any calculation you do in asymptotics, the answer is going to be built out of these three basic building blocks. So this is actually, believe it or not, a theorem, proofs from Ecalle and then there's Aschenbrenner and company, that a formal trans-series that is built out of these objects and including all iterations to all orders is actually closed under all operations of analysis. Now, I'm not going to talk about that. That's a big theorem, and I'm not even qualified to talk about the proof of that theorem. But I'm going to take it as also as motivation, because there's a deep conjecture here that people take quite seriously, that in fact, in the physical world, the mathematical physics world, this trans-series structure is going to be practically sufficient for all asymptotics that we might try and do. So now that's a little bit vague. Let me make it a little bit more specific here. So one way to think of this resurgence and resurgent trans-series, think of it as a unification of perturbation theory and non-perturbative physics into one object, which we call a trans-series. So think of taking some perturbative series, which very often in physics, but not always, but very often is an asymptotic series if we're doing perturbation theory. Generalize that to a trans-series. And this is what a trans-series looks like in most semi-classical calculations. So this does not have the same iterations, but this is what semi-classical trans-series look like. You have, say, perturbative fluctuations, some formal power series. Again, as I said, it's often just a formal asymptotic series. But then there might also be contributions due to tunneling, which we would call instanton effects, which are these exponentially suppressed type factors. I've normalized the thing here to 1 just to keep the equation simple. And there will be multi-instantons, so there'll be powers of this due to tunneling back and forth, or through different barriers. And the other object is that when you do a dilute instanton gas calculation, you actually have at the 2-instanton level, you have interactions between instantons and also instantons and anti-instantons, and they generate logarithmic terms in the small coupling parameter. And I'll call them quasi-zero modes because they're related to not zero modes related to asymmetry, but modes that are suppressed compared to the basic perturbative band gap. So the underlying idea here is that this trans series is actually well-defined under analytic continuation in the way that an asymptotic series is not. So for example, the asymptotic expansion of the digamma function, the derivative log of the gamma function, has an well-known asymptotic expansion, the Stirling expansion, along the real axis. But that asymptotic expansion doesn't tell you about the reflection formula, and it actually violates the reflection formula, which is what you use to analytically continue that function throughout the complex plane. But there's a generalization of that asymptotic expansion that includes the exponential terms that restore or satisfy the reflection formula. And that would be the trans series representation of the digamma function. It doesn't have any logarithms in that case, but it's built out of these two terms. So that's a simple example. That's the basic idea. Now, if that's true, if it's true that if you just took the perturbative fluctuations and it didn't satisfy some global analytic constraint that you had, but when you restore the, say, exponential contributions that are produced by these Stokes transitions, if that then restores the proper analytic continuation properties, the only way that can happen is if the coefficients for the expansion in this direction and in this direction, they must be related to one another. Because these guys are repairing something that's missing from here and vice versa. So just at the outset, by necessity, if it really is true that this trans series is well defined, then that implies that there is a precise relation between the perturbative expansion and these non-perturbative terms. So I'm going to show you several examples of this phenomenon in detail as we go along. So these ideas came from the world of dynamical systems and ordinary differential equations and have been studied in great detail for partial differential equations, difference equations, applications in fluid mechanics. And there's also been some and a growing body of work in the realm of quantum mechanics, matrix models, field theory, wall crossing phenomenon, etc. There are rigorous results in the differential equations and difference equation regime. In the realm of quantum mechanics and matrix models and field theory, there are less is known precisely, but there are many, many interesting examples, and I want to give you a flavor of that. So the idea to connect with my original motivation is that the path integral has these problems with being defined under analytic continuation of its parameters. If you just make a formal expansion of this around some saddle point, you generate this. And since the trans series has the opportunity to be well-defined under analytic continuation, maybe it makes sense to actually define the path integral constructively as a trans series. And that's the underlying idea to explore here. And there's been a lot of related work by Maxim Kontsevich, also seeking a resurgent definition of the path integral, and very beautiful examples in specific quantum field theories, known as Jones-Simons theories, recently in the work of Kukov, Marino, and Kucherov, and many others. But I'm not going to talk about the quantum field theory applications today. I want to give you a specific example from quantum mechanics and in matrix models where everything's under complete control. So where does this funny word resurgence come from? It's from a quote from John Ecalle, and I have a picture here to keep in mind. The idea is resurgent functions display at each of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or resurge in a slightly different guise, as it were, at the singularities. So look at this picture. Each of these raindrops is supposed to represent a saddle point, a critical point, a singular point of whatever problem you're studying. And the cylindrical ripples around each raindrop are the fluctuations around that saddle point. And the idea is in a standard problem, there'll be many of these saddle points in general, and each of them will be able to be studied locally as an expansion around this point. And the idea of resurgence is that there's an extremely precise network of relations between the fluctuations around this saddle point and this one and this one and this one. And that this is actually a very general phenomenon. And just realizing that that's a possibility opens all sorts of questions that hadn't been studied before. And the real question is, does this actually apply to all problems in physics, such as an infinite dimensional problem like a path integral? And that's what I want to talk about. So another piece of the machinery here is Parallelecol summation, which I think everybody here is very familiar with, but let me just say a few words. If you generically have a factorially divergent series, one of the ways to control this is to make an inverse Laplace transform, a Borel transform, to a series where you've divided out the basic factorial growth. So this transform function now has a finite radius of convergence. And so formally, term by term, taking the Laplace transform of each term here, the integral over t just produces a factorial, so you go back to the previous series. So you haven't gained much if you just do it term by term. However, if you know something about the analytic structure of this guy, such as where its singularities are, what type of singularities they are, then you have really gained something. And this upgraded form of Parallelecol summation, known as Parallelecol Summation, deals with two of these main problems. One is, what happens when the singularities of this are on the contour of integration? So it turns out there's a formalism called medianization to control this rigorously. And the so-called these relations between these different saddle points, this Borel transform function will have different singularities, and those are the saddle points. Using a technique, formalism known as alien calculus, there is a network of bridge equations that relate the behavior at the different singularities. And at a simplistic level, you can just think of this as contour deformation in the Borel plane, relating the behavior around one singularity to the behavior around another. But it's deeper than that. The point is that if you're presented with a physical calculation in, say, perturbation theory, where you have some formal series, you want to make sense of that series. And the first step in this is to realize that the Borel transform is a much more physical object that tells you something about what's going on. And so the singularities of this really are the non-perturbative physical objects in the problem. So again, to continue with a simple example, let's go back to the area function. So the area equation is very simple, linear equation, two independent solutions. Here's their standard asymptotic expansion at large x. So there are the two WKB exponential factors, and then you see that there are two factorials on top, one on bottom, so there's factorial growth here. And the issue is the difference between the area AI and BI. If you just look at the asymptotic expansion, you would think that if you changed x to the 3/2 to minus x to the 3/2, that would just be going between these two. So rotating the phase of x by 2 pi over 3 at the level of the asymptotic expansion looks like these two black pieces of this equation should be equal to one another. But of course, as I mentioned before, that's not true. There's a non-perturbative connection formula. There's this additional exponentially suppressed piece that's missing if you just look at the asymptotic expansion and make a formal rotation. So this is a very simple example. We're all familiar with it, I think. The way it shows up in the Borel representation, remember, if you take the Borel transform, you're basically dividing these coefficients by n factorial. And so you see this is a simple problem where the Borel transform is just a hypergeometric function. And we know the singularity structure of the hypergeometric functions. So this integral here now would be, this is the Borel representation of this formal series. And now if I rotate x to change the sign of x to the 3/2, I can compensate that by rotating in the t-plane, the contour of integration. But eventually I'm going to hit the cut of this Borel transform, which goes from -infinity to -1. However, I know the jump across the cut. I know the dispersion relation for the hypergeometric function. So this is a situation where you know the analytic properties of the Borel transform, and it's exactly that jump across the cut that produces this exponentially suppressed piece. So this then is the challenge. Can we use these ideas of Borel transforms at the level of not just a simple linear problem, but for a nonlinear ODE, and eventually for some infinite dimensional set of equations? Another way to see these so-called resurgence relations between the different fluctuation points that turns out to be generic. Remember, the Airy function was the exponential integral with a cubic in the exponent. So there are two saddle points, the two WKB contributions. And the coefficients of the expansion are just here, these factorials, and the low order terms of this. Now it turns out if you pick one of these, let's say the plus sign for one of the saddles, and you expand these coefficients at large order in the expansion, there's a factorial growth, there's a power, which happens to be the difference between the two exponents, the 2/3 and the -2/3 in the exponent of the Airy function. And then there are power law corrections. And you will notice that these numbers here, when it's suitably normalized, are exactly the expansion coefficients around the other saddle point. So it turns out this is generic. It's a generic feature of exponential integrals. It's not widely known. But if you take the expansion at large orders of the fluctuations around one saddle point, then the subleading corrections to the large order factorial growth is actually directly related to the low orders of the fluctuation expansion around another saddle point. And here there are only two, so they're related back and forth to one another. It turned out this is generic. You can, if this is new to you, I urge you to pick at random your favorite special function and just have a look at the large order growth of the expansion of the fluctuation expansion coefficients. And this behavior has been observed experimentally, so to speak, by actual calculations in the infinite dimensional context. And I'll show you a few examples of that as we go along. And this is one example of Ecalle's bridge equations, that the fluctuations around one saddle are directly and quantitatively related to the fluctuations around another. So let me go to the first example. So here's a very familiar problem, the Matthew equation, which I write in its sort of mathematical form here. And here are the pictures that I'm sure you're all familiar with also. The stability regions as a function of this parameter Q and the parameter A. And there are these stable and unstable regions that are very narrow at this end and then broaden out. You can also think of this as a quantum mechanics problem where this is a potential, Q is like 1/h bar squared, and with suitable scaling, this is the energy eigenvalue for a periodic potential. And we all know that this has bands and gaps in its spectrum, which is what's pictured here, the periodic and anti-periodic solutions at the edges of the bands and gaps. Now here are the bands. So let's look a little bit more deeply at this problem. So here I've written it now in its quantum mechanical form. And here I'm plotting the energy as a function of h bar, which is somehow related to the strength of the potential, if you like, and also the label that labels which band I'm talking about. So just to orient yourself, here's the coupling strength, here's the energy. The dotted lines here, horizontal dotted lines, are the upper limits of the cosine potential, plus or minus 1. And so you see that deep down in the potential, the bands are exponentially narrow, and they become broader as you increase h bar. So increasing h bar is increasing the height of the potential. So, but you also see that as a function of h bar, this is h bar over 2, 3 halves h bar, 5 halves h bar, 7 halves h bar. These are the harmonic levels in a given well that broaden out and become broader bands. And we all know that this exponential splitting here of the band, of the sort of discrete harmonic level into a band, is related to tunneling between neighboring wells, and this is known as a real instanton effect. But what is less well known is that the very narrow gaps here, very high up in the spectrum, well above the top of the potential, these are due to complex instantons, because of course in this region, there are no real turning points, but there are complex turning points. And if you evaluate the action on a solution that goes between these complex turning points, that actually gives the gap splitting. So this much is very well known. And you can also see from looking at this that there's an interesting transition happening here, that this one instanton type approximation, exponential approximation, is very good here. But as you approach the top of the barrier, it's a very bad approximation. You need to sum over all instantons. And you'll also notice, if you look carefully, that the width of this band is equal to the width of this gap. And the width of this gap is equal to the width of this band, and so on. And there's an actual Stokes transition at this point, where the physics is driven by real instantons here and by complex instantons here. So we should be able to see this at the level of a trans series. So that's what I'm going to talk about now. So there's a lot of work here from, originating in things we knew from solid state physics, but there are real rigorous theorems about bandwidths and gap widths. And the basic result is that for bandwidths, there's an exponentially small splitting, is the leading contribution, with a prefactor, which is some density of states factor, which is the derivative of the energy with respect to the level number. And the gaps, similar but related now to actions going between complex turning points. So this much is well known, but looking at this problem through the eyes of resurgence, you would be tempted to relate or to study the fluctuations around this, because this is identified as the leading non-perturbative saddle. So resurgence tells you that this thing here should be somehow related to the perturbative expansion. And people just simply never thought of this question without thinking in terms of these resurgence relations. There's something very interesting happens. So let's look now at E plus minus. So these are the upper and lower edges of a band. And there's the formal perturbative series. So you take the nth harmonic level inside a deep well, and you do perturbation theory, you get a formal series in H bar. The coefficients are polynomials in the level number, n. So that's a simple calculation. Then there's these exponential splitting with some known calculable prefactor. But then there's this 1 plus order H bar stuff. So this itself is a formal series in H bar, again with coefficients that are simple functions of n, in fact, polynomials in n. And the amazing result is that this can be completely expressed in closed form in terms of this to all orders in H bar. So here's the generalized version of this expression here, which is just leading order in H bar, is that in fact, this formal series, which is itself an asymptotic series, is equal to the n derivative of this formal series. Remember, the coefficients are just simple polynomials in n, so this is well defined. And then there's this exponential factor related to this particular integral of this density of states factor with some normalizations which take care of this prefactor business. And what's interesting, this is true to all orders in H bar and for any n in the band region. And there are hundreds, if not thousands, of papers written about the Matthew equation, and this could have easily been studied several hundred years ago, probably. But it doesn't really come as a natural question without looking at this problem through the view of trans-series and resurgence. Moreover, there's the 2 instanton, 3 instanton, 4 instanton, etc. Contributions. And at every order in that exponential expansion, there are series which can be expressed all in terms of this, in closed form expressions. And at the 2-instanton level, you start generating logarithmic terms, but they simply don't fit on the slide here. Okay, that's interesting maybe. Well, if you look at the gap region, in the gap region, so this is now an expansion at large h bar. Again, the expansion coefficients are functions of the gap label n. Interestingly, this is now not a formal series. This has a finite radius of convergence. Nevertheless, there is splitting. It can be traced back to poles in the continued fraction representation here. And this fluctuation is related to this fluctuation in exactly the same way that this is related to this, even though they're now convergent expansions. So this is a very clear example of this resurgent behavior, that the fluctuations around a non-trivial saddle point, which would be given by this or by this for the complex saddle or for the real saddle, is related to the fluctuations around the trivial saddle, which is the ordinary perturbation theory, just expanding around the bottom of the well. And moreover, as you go from the gap region to the band region and back again, this trans series completely rearranges itself in structure because it's being dominated in one region by real saddles, if you think of it in path integral language, and in the other region by complex saddles. And as you approach the transition point across here, at this point here, it's not exponentially narrow, and you have to somehow resum all of these plus dot dot dots here, and the 1-instanton approximation is no good. But when you resum them and go across this transition point, it's a nonlinear Stokes phenomenon where at all orders you have this rearrangement from real saddles to complex saddles. And so this is the first example I wanted to show you where this raindrop picture really works, in the sense that we're now talking about a problem with an infinite number of saddles because it came from an infinite dimensional exponential integral. So there are an infinite number of these dots. And remarkably, the fluctuations around any given one of these can be expressed in closed form in terms of the formal asymptotic expansion around the sort of trivial raindrop. And clearly you can just pick one as your starting point, but the perturbative expansion is the natural starting point. So this didn't need to happen, right? It wasn't obvious at the start that these results from the finite dimensional world of Picard-Lefschetz for exponential integrals and from the finite dimensional world of, let's say, linear differential equations, that these would actually still apply when you go to this real infinite dimensional world of quantum mechanics. So there are many examples of this phenomenon. I just showed you for the periodic potential. There are many examples where this has been verified. There are some proofs of what class of Schrödinger type problems this applies to, but there's really an opportunity here for rigorous proofs from mathematicians and mathematical physicists. There's a lot to be done here. Okay, so that's the first example. Now, if we think about going to quantum field theory, well, in quantum mechanics, the basic source of the divergence of perturbation theory is one of combinatorics. That just the number of diagrams you have to calculate grows very fast, factorially fast. But in field theory, things are less clear because the coupling is actually a running coupling. And so particularly in asymptotically free theories, it's still quite mysterious how we would upgrade this sort of analysis to quantum field theory, even though there are some particular explicit calculations in certain special quantum field theories related to integrability. So let me show you a sort of halfway picture where we can still do things completely, which is the world of matrix models. So I'm going to use one particular example, this Gross-Witten-Wadia unitary matrix model, which was developed as a lattice representation of two-dimensional Yang-Mills theory. But it turns out it has quite universal application in lots of problems, both in mathematics and other problems in physics. So think of an integral over n by n unitary matrices, weighted by an exponential factor. And this is basically supposed to be representing a cosine type function, u plus u dagger. And there's a parameter n, which is the dimension of the matrix. And there's another parameter t, which is the, say, the 't Hooft coupling. So this is a, you can think of this as a partition function, or as a, and in the large n limit, the infinite n limit, this is trying to be an infinite dimensional path integral. So think of this partition function as a function of coupling n. And what was discovered by Gross and Witten and by Wadia is that at n equals infinity, there's a third order phase transition at t equals 1. So actually they normalized it somewhat differently. Their phase transition was at 2, but it's more convenient to rescale things to put it at 1. So here's a picture from the paper of Gross and Witten of the specific heat per degree of freedom showing a kink at this phase transition. And this kink appears at n equals infinity. Now this model has lots of applications in large deviation theory and probability, random matrix theory, all sorts of places in mathematics. It has an exact representation. You can just do these integrals. These are integrals over eigenvalues of the matrices, and there are lots of techniques relating orthogonal polynomials to these eigenvalue integrals. And you can actually write this partition function in closed form as a determinant where the entries are modified Bessel functions, where the index of the modified Bessel function is, the row minus column index here. However, determinants are difficult when n becomes large. That's not a very efficient way to study the large n limit, particularly if you want to look for exponentially small behavior at large n. And what a lot of the initial work was done focusing in the so-called double scaling regime, where you zoom in on this particular transition point. But I want to be able to describe this at all n, and as n approaches infinity, but for all n and for all t on both sides of the transition. So let's see how this problem looks if we use resurgence. So knowing that resurgence is best developed in the world of differential equations, it makes sense to use a particular result that there's a so-called order parameter, which is the expectation value of the determinant of u. And it's been known for quite some time that this function here satisfies a particular nonlinear differential equation, which is in the Penave-3 class. So for experts, this is related to the Okamoto form of the Penave-3 equation with a particular choice of parameters. If that doesn't mean anything to you, don't worry. Here is the nonlinear equation. It's second order. The derivatives are with respect to the coupling, the 't Hooft coupling. There's some linear pieces, and then there are some nonlinear pieces. And you see that n, which is the size of the matrices, only appears in this equation as a parameter. There are other formulations written as difference equations and differential difference equations, but this is purely a differential equation, and n just appears as a parameter. Okay, when I call this an order parameter, what I mean is knowing this solution, it's essentially the integral of the log of the partition function. So knowing this solution, you can immediately calculate the free energy, the partition function, specific heat, whatever you want. And it satisfies the simplest form of nonlinear equation. So the large n expansion is typically given as a formal expansion in inverse powers of n. The coefficients still depend on t being the 't Hooft coupling. But actually, the formalism of resurgence suggests that, in fact, this is just the beginnings of a trend series where there should also be exponentially suppressed terms, exponentially suppressed at large n, with some coefficient here, which is also a function of t, multiplied by a fluctuation which is itself a formal series in inverse powers of capital N with coefficients that are, again, functions of t, and so on. And Resurgent suggests that these guys should be related to these guys, and these guys should be related to these guys, and so on. But here, they're not just numbers, they're functions of t, and these relations should still hold. So this is something worth exploring. And moreover, we know that since there's a phase transition here, we expect that this trans series will completely rearrange itself as t crosses 1, this value of 1. And this should be interpreted as a Stokes transition in the infinite dimensional version of the partition function. So let's see how that works. Well, the first term is very easy because given the differential equation, we just look at this equation. When n is infinite, the only relevant pieces are these terms. And now you see that it's just an algebraic equation that determines delta to be square root of 1 minus t, and no derivatives at all. And knowing that, you can then just put this ansatz in here, and it's a simple matter to then recursively generate these coefficients. That's fine. But you see that if you insert an ansatz which includes also these exponentially small terms, and you grade according to these exponentials, then you see that this thing here, the first exponential term, will satisfy a linear equation. And moreover, it will satisfy a linear homogeneous equation, which you can then easily solve from the differential equation. And in fact, you get a tower of linear equations for each of these contributions. And it can be treated just as an ansatz that you grade the expansion according to these exponentials. So let's see what happens. So here's that overall simple square root of 1 minus t. There's some expansion in inverse powers of n that turn out to be even powers. And these coefficients can be just generated trivially to as many orders you want with Mathematica or Maple or whatever. But then there's an exponentially suppressed piece. It came from a homogeneous equation, so there's a parameter there. That's called a trans-series parameter, and it's related to the boundary conditions because this was a second-order differential equation. The differential equation tells you what this function is. It's this weird-looking function, but it's just a simple solution of a differential equation. And then you can generate all of these coefficients, again, to whatever order you desire. And so we can study the large order growth of these coefficients. And indeed, this factorial growth, the power law that goes with the factorial growth is related to this exponent. That's exactly what Borel summation tells us should happen. And there's some prefactors here related to this term and this normalization term. And then there are subleading terms where instead of gamma 2n minus 5 halves, the next term is gamma 2n minus 7 halves. It has an extra power of the action, and it has some coefficient. And again, you can simply calculate that by looking at the large order growth of these coefficients here. And then Resurgent would tell you, remember these large order, low order relations that I showed you for the area function, these subleading corrections here should be related to these coefficients. Well, indeed, you can calculate these coefficients again iteratively, and it's very simple. And you see that the first term in this low order expansion around this one instanton term is exactly the same function of t as the first subleading correction at large order of the growth of these coefficients. So that's what I called before a generic example of Ecalle's bridge equations relating the behavior of the fluctuations near one saddle to the behavior of the fluctuations near another saddle. So of course the story is much deeper than that, but this is a sort of glimpse of this phenomenon of resurgence relating these fluctuations to these fluctuations. And of course it continues plus dot 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 to all orders in this exponential expansion. So that's on the weak coupling side, where t is less than 1. So in this picture here, remember I've rescaled. So that's on this side. This is the infinite n limit here, but this is what happens at finite but large n. Now let's look at the other side, this phenomenon here can be related in the original integral over the eigenvalues of the unitary matrices. This phenomenon here can be understood in terms of the real eigenvalues of the Hermitian matrix related to the unitary matrix. But now when we go to strong coupling, the behavior is completely different. On the strong coupling side, when t is bigger than 1, the leading term is already exponentially suppressed. And you get this again directly from the differential equation. And the strong coupling action is this function of t. It's a different function of t. It agrees with the other one at t equals 1, obviously. And there's an expansion in inverse powers of n with some coefficients. And ... There's 2 instanton, 3 instanton, etc. And these guys are related to the fluctuations around the other guy, and so on. This structure of the trend series turns out to be related to complex saddle points of the original eigenvalue integrals. But it's complex saddles in an infinite dimensional context. What's happening here is we're crossing this phase transition, and as we approach it from the weak coupling side or from the strong coupling side, we need to include all of the exponential terms on one side and all of the exponential terms on the other side. And at the transition, there's a sudden jump, but there's a jump at each of the exponential orders. So it's this nonlinear infinite dimensional Stokes phenomenon. Interestingly, in this case, you can actually relate it quite explicitly to the Airy function again, because this structure here is actually related to the asymptotic behavior of some Bessel functions. And those can be formulated in a uniform large N expansion in terms of, again, the Airy function, but the Airy function with argument that is related to this. And this actually gives a representation of the free energy and specific heat and whatever that are much, much more accurate near the transition point, t equals 1, at finite values of n. And it really is analogous to the idea of uniform WKB, where if you're trying to solve the Schrödinger equation, instead of substituting an exponential ansatz for the wave function in normal WKB, you might substitute near a turning point an Airy representation, which smoothly goes through the turning point. And this is like an infinite dimensional version of this. And it's consistent with the double scaling limit of this original Painlevé 3 equation down to Painlevé 2. Okay, so that's the second example I wanted to show you. And the moral of this example is that we can, in fact, formulate and study a trend series where there's not just one parameter, or two parameters, and we can simulate the behavior we expect for a, say, thermodynamic limit of a phase transition. Thermodynamic limit here being the infinite size limit of the matrices. And we see that it is indeed possible to, first of all, observe the phase transition at finite, forming at finite n, and to be able to see how the trend series reorganizes and restructures itself as you cross the phase transition, and to interpret that as an infinite dimensional nonlinear Stokes phenomenon, as I hinted at the beginning of the talk, as motivation of a way to understand phase transitions in path integrals. All right, so I have maybe 5 to 10 minutes left. So let me turn to one final topic. So this is based on a series of papers with Ovidiu Costin, who I think is in the audience. Hi, Ovidiu, who is an expert in asymptotics and also in resurgence. And so this addresses a slightly different question, but I think you'll see in a moment why it's related. Think of now a really difficult problem, not some sort of integral problem where we have nice integral representations or we have nice simple differential equations to play with. But just think of a really hard problem where maybe the only possible thing you can do is to calculate some number of terms in perturbation theory or in some asymptotic expansion. And the number may be 5, 10, 20, if you're lucky, maybe 100. Depends on the problem, right? But some finite number of terms. So, the question arises, is resurgence going to be useful in this context? So one way to understand resurgence is that it suggests that local analysis of perturbation theory somehow encodes, to some degree, exponentially suppressed non-perturbative information, global information, in a way that's characterized by these Ecalle bridge equations. So if that really is true generically, as many people believe in the community, if that's true, then maybe you can design better extrapolation methods that take advantage of this. And so a more precise question would be, how much global information about a function can actually be extracted, decoded from a finite number of perturbative coefficients? And the key here is that resurgent functions tend to have some symmetric, orderly structure in the Borel plane. In principle, your Borel transform could have singularities in all sorts of places without any structure. But in practice, in most problems in physics that we are aware of, these singularities tend to have some structure in the Borel plane. They're either repeated in integer things in various directions. They don't tend to be randomly distributed. So can we develop tools that somehow take advantage of this? And if so, they should be now much more precise and much more amenable to analytic continuation. So let's do an example. So this is a famous example, one of the Penave equations, the first Penave equation. It is well studied in physics in the context of matrix models of 2D quantum gravity, but it's well studied in its own right. It's the simplest and yet in some ways the most difficult of the 6 Penave equations. It doesn't have any parameters. So here it is. There's just a quadratic nonlinearity. Looks fairly innocent. Now, it's fairly easy to see that as x goes to plus infinity, looking for a smooth solution, we balance this term against this term. So there's this overall square root of x over 6 behavior with a plus or minus. I'm going to choose the minus sign. And then it's a simple exercise to check that, including the derivative term, you generate an expansion in inverse powers of x to the 5/4, or actually x to the 5/2. Put 2n here. So this is the form of the asymptotic expansion at x goes to plus infinity along the real positive x-axis. And here are the first few terms. And you can see two things. They're alternating in sign, and they look like they're growing fast. In fact, they're growing factorially fast. It's also a simple matter to generate lots of these coefficients just by ansatz. You can set up a simple recursion formula, which will generate hundreds, thousands of these coefficients. But what's also known about this equation is that in the negative x direction, there's a wedge of width 2 pi over 5, in which this function has this meromorphic pole expansion. It has a second order pole at some location, which is as yet not known. And then the expansion around it eventually includes one other parameter, the other boundary condition parameter. And all the other terms are expressed in terms of this guy and this guy. So that's what's known. This dates back to work by Penave and Boutroux and people 100 years ago. So if you look at a picture, it turns out this equation has an inherent 5-fold symmetry. It's easier to check just by rotating by 2 pi over 5. This line about which we're expanding is one of these anti-Stokes lines, but there's a Stokes line at 2 pi over 5, an anti-Stokes line at 4 pi over 5. Here's this pole region, and then a Stokes line here. So remember, this is as we rotate the phase of x, there's going to be all sorts of very complicated, interesting changes as we cross these transition lines. There's a conjecture from Dubrovin in studying some KdV properties in the nonlinear Schrödinger equation that the poles only appear in this wedge here. And this was proven some years ago, maybe 5 years ago or so, by Ovidiu and the student Huang and Selatanbit. So the question I want to ask is, suppose now you just start with an asymptotic expansion out here and some finite number of terms of the asymptotic expansion out there. Do those coefficients know anything about this global structure? And if so, what do they know and how much do they know and how can you use it? And so these directions are the most interesting directions. These are the phase transition region. So do these, just these coefficients here, know to turn this expansion into this expansion? Well, the answer turned out to be yes. So here's a plot of the poles of the solution to the equation, which was generated from an expansion at x equals plus infinity. So this plot is using 200 terms of that expansion, and we can track the solution all the way through the Stokes transition and through this anti-Stokes transition into a region. Here are the poles, and they match exactly the asymptotic expansion coming from the analysis of Ovidiu himself in this Penové equation. If you just give me 10 coefficients around x equals infinity, we can locate the first 3 of these poles. Okay, so it depends on the amount of information that you provide, but it is possible using these ideas from Resurgence to develop an extrapolation tool that can go from here all the way around here through a Stokes transition, through another Stokes transition, into a region in which the solution has a completely different expansion. So this is analogous. Now think back to the quantum mechanics example of the Matthew equation and also this matrix model, where this trans-series type solution restructures itself as it crosses a transition. But here we can see it already with some surprisingly limited amount of input information. And there's also significant improvement in precision. So why is this happening? So it turns out that if you assume that the function you're looking for is a resurgent function, then you have some information about the underlying Riemann surface. And it turns out that there's an optimality theorem of what's the best way to minimize errors on the Riemann surface. And it's using a uniformizing map and then re-expanding. So that's true. In the case of these Penové, we know the surface, and so we know the map, and so we can do things in more detail. These uniformizing maps actually allow you to do even more, to actually go onto higher Riemann sheets. But I think the most practical consequence of this is that you get dramatic improvement in analytic continuation, and especially near the interesting points, which are these transition points. So for example, there's one idea here is we call singularity elimination, is that if you want to know where a particular singularity, the next thing you would like to know is what type of singularity it is. And it turns out you can set up a resonance test using these exponential precision ideas underlying Resurgence to simultaneously tune the location of the singularity and its nature using a resonance idea. So it's much, much more precise than standard sort of ratio test ideas. All right, I think I've run out of time now, so let me just go to my conclusions. So these ideas of Resurgence may be unfamiliar to people, but sort of globally think of it as a systematic formalism that aims to unify perturbative and non-perturbative expansions using these objects called trans-series. And the overall idea is that if treated properly and developed properly, these should be able to combine perturbative and non-perturbative information in such a way that the trans-series itself is well-defined under analytic continuation. And the idea is to then use that to study path integrals in quantum mechanics or statistical mechanics systems or in quantum field theory. And so the motivating conjecture is that the trans-series can be used as the steepest descent expansion of a path integral. And if you keep all of the terms, both non-perturbative and perturbative terms, you can actually treat analytic continuation of the path integral. And I've shown you some examples. I should mention that what I haven't talked about, there's been a lot of progress in integral quantum field theory and in topological string theory. These are cases of special theories where sometimes the path integral can actually be done and reduced to a matrix model problem. There's also been actual numerical progress of people studying the sign problem, which remember previously was inaccessible using Monte Carlo techniques, using these ideas of somehow deforming the infinite dimensional path integral into these steepest descent contours known as Lefschetz thimbles. And just finally, I think there are many surprising results here that are not quite rigorous, but quite convincing. And there's a lot of room for further conjectures, and there's certainly a lot of room for rigorous proofs. And if you're interested, you can look at the conference organized by Maxim Kontsevich a couple of years ago now at IHES, which has some talks about some of the applications. So thank you.
Well, thank you very much. That was very interesting. Are there questions?
I have a question.
Yes.
What is the difference between a Stokes line and anti-Stokes line?
Well, a Stokes line is where there's exponential growth or decay, and anti-Stokes would be where it's oscillatory.
Okay. And another question. Do practitioners start to use resurgence for actual computations?
Well, so here's an example of actual computations. So what has been done using lattice Monte Carlo? So there's the Bose-Gas problem of a complex scalar field, which at finite density has a sign problem. There's even the Euclidean formulation has an oscillatory action. So a complex action. So standard Monte Carlo techniques simply fail at the beginning. So what people have done is to try and set up a gradient flow method to define the steepest descent contour in this infinite dimensional space, and then to study that with Monte Carlo. And so that has now been applied to this 4D Bose-Gas problem successfully. It's been applied to the string model and the Turing model, and there's been some application successfully. So these are, they're not QCD, but they're non-trivial quantum field theories with phase transitions. And people have applied it also to Hubbard type systems, Hubbard model type system. But it's relatively early days in this. So it's really, I think the phase at the moment is what I would call exploratory, but there are real serious lattice calculations. There are also studies of Renormallon behavior in quantum field theory. There've been a lot of works in Chern-Simons theory where it's extremely explicit because the saddle points are flat connections on the manifold. So a lot is known about them from differential geometry. And these types of resurgence relations are observed on many 3D manifolds. So there are real calculations. We're not yet at the stage of being able to study something really difficult like Yang-Mills or QCD, but there's a lot of work in that direction at the moment.
Thank you. Further questions? No more questions?
Still, I have another question. In most talks about resurgence that I heard, there are examples from the Penn-Levy equations. Is it a coincidence, yes, or is there anything special about Penn-Levy that makes it?
Okay, so let me make a few comments. So first of all, the most important comment is that integrability is not essential. Resurgence is much stronger than integrability. You don't require integrability to see this resurgent behavior. So that's the first comment. But you are right that many of the examples that people have studied in detail have been from this integrable world. And I think it's really just a consequence of the fact that in that case, there is rigorous information with which to compare. So for example, in these PNV1 that Ovidio and I studied, there was genuine information about the connection formulas between different regions that we could check whether our extrapolation satisfied that. If you take some other system, there's less information with which you can compare. So I think that's part of the reason that a lot of the examples you've seen, I think people are still in this method of working, of trying to see how far this can go. And the natural place to start is in places that are better understood. But let me be clear, it's not essential to have integrability. It just makes the calculations easier and more explicit.
So maybe I have a follow-up question.
Yeah,
Sure.
Hi, Patrick.
Hi, Gerald. Hi. So you say integrability is not required, but
No.
is something else possibly is required? I mean, do you think that there's, just to see this sort of behavior, I kind of missed.
Yeah. So this is where things start to get a bit fuzzy, at least in my mind. So maybe Ovidio can state all the fine print, but within certain classes of nonlinear differential equations, both ordinary and partial, this structure is guaranteed, and integrability is not a requirement of that. Okay, so it's certainly a bigger class. And that's easy to check. You can just take your Painter equation, you can throw in a deformation that breaks integrability, and you see that it's all still there. How far it will go when you go to the infinite dimensional world is, I think, the real problem. Now, from the point of view of quantum field theory, this is not such a disaster because, conditions like having some, meromorphic or well analytic type action functional, that's not a big restriction. Right? Where the field theories we're interested in aren't going to violate that. The thing they're going to violate is being infinite dimensional.
Thank you. Further questions?